When we think of sugar, we usually picture those little white crystals, right? Super simple. But it turns out at the molecular level, even the most basic sugars, like glucose, are leading this incredible double life. They're
Mm.
total shapeshifters, and that constant transformation is, believe it or not, fundamental to how life itself works. So that brings us to the big question. How in the world can one single molecule have two totally different shapes? I mean, it sounds like it breaks the rules of chemistry, doesn't it? Well, that's exactly the mystery we're going to unravel today. And here they are, the two faces of glucose, right next to each other. On the left, you've got the open chain form. It's basically a straight line of carbon atoms. But then look to the right. That is the exact same molecule, same number of atoms, same everything, but it's curled up on itself to form this tidy hexagonal ring. So how does it do that? To get it, you first have to really wrap your head around the idea that this one molecule genuinely has two different identities that it can just switch between. Yeah, this isn't some rare, quirky exception. It's a core feature of these sugars. The source material is super clear on this. Glucose is always in a state of flux, in an equilibrium between these two structures. And actually, that ring form, that's the one that's most common and most stable in solutions, like the ones inside our own bodies. All right, now for the main event. Let's actually watch how this transformation happens. How does a straight line become a loop? It's kind of like a beautiful little piece of chemical origami. Okay, so take a look at the open chain here. The real magic happens between two key players. You see that carbon atom up at the top, the one double bonded to an oxygen? That's our carbon 1. Then, way down at the other end, you've got that little OH group, the hydroxyl group, hanging off of carbon 5. Well, these two ends are about to get real close. So how do they connect? They do it by forming this special bond called a hemiacetal. What happens is the oxygen from that hydroxyl group on carbon 5 basically reaches over and attacks the carbon at the other end, carbon 1. And when it connects, it creates this new COC bridge that literally clasps the two ends of the molecule together. And voila, here's the result. You can see it plain as day. The chain that was once a straight line has now buckled into a ring. And that new bond we were just talking about, the one between carbon 1 and the oxygen from carbon 5, that's our hemiacetal. It's the lock that holds the whole ring structure together. Just when you think you've got it, the plot thickens. Because when that ring snaps shut, it can do so in one of two slightly different ways. And this tiny, tiny variation creates two new versions of the glucose ring. This distinction might seem small, but in biology, it's a really, really big deal. Let's go back and focus on carbon 1 for a second. Before, it was part of a flat group. But now that it's in the ring, it's suddenly holding on to four different things, which makes it what chemists call an asymmetric center. And this special carbon gets a new name, the anomeric carbon. And because of this new setup at the anomeric carbon, the little hydroxyl group attached to it can either point down or it can point up relative to the ring. These two different spatial arrangements, up or down, are called anomers. Now look at this, because the difference is so subtle it's amazing. On the left, alpha-D-glucose. On the right, beta-D-glucose. Look really closely at that highlighted OH group on carbon 1. See it? In the alpha form, it's pointing down. In the beta form, it's pointing up. That's literally the only difference between them. So here's the official rule of thumb so you can always tell them apart. First, find that little CH2OH group that's sticking up from the ring. If the OH on our special anomeric carbon is on the opposite side, it's alpha. If it's on the same side, it's beta. This tiny flip is literally the difference between starch, which our bodies can digest, and cellulose, wood fiber, which we can't. Mind-blowing, right? Okay, so we've got it. Sugars form rings. But do they always form the same size ring? Nope, not at all. Turns out the two most common ring sizes are these right here. A 6-membered ring, like the hexagon we've been seeing with glucose, is called a pyranose. But sometimes they form a 5-membered ring, a pentagon, and that's called a furanose. And you'll notice both of them have an oxygen atom built right into the ring itself. So yeah, it's really all about counting the atoms that make up the ring. Pyranose, 6 members total, 5 carbons and 1 oxygen. Furanose, 5 members total, 4 carbons and 1 oxygen. Let's see what this looks like with a couple of real-world examples. And here we go, connecting those shapes to actual sugars. Like we've been saying, glucose loves to form that 6-membered pyranose ring. But fructose, the sugar you find in fruit, it actually prefers to form the 5-membered furanose ring. So you've got two of the most common sugars out there, and each one has its own favorite shape. Whew. Okay, we've gone through a lot of molecular details here. Chains, rings, alphas and betas, pyranoses and furanoses. But at the end of the day, why does any of this actually matter? Well, the source material itself asks the perfect question to tie it all together. Why is it so important to study all these different forms? And here's the answer, straight from the source. It's because the shape, the form that a sugar takes directly controls its properties, how it tastes, how it reacts chemically, and crucially, how our bodies can or cannot use it. The form isn't just a tiny detail, it is the defining feature. It all boils down to what is maybe the most important rule in all of biology: structure dictates function. The exact same molecule, glucose, linked together in the beta form, creates the tough, rigid structure of a tree trunk. But link those same glucose molecules in the alpha form, and you get these soft, energy-packed starch inside a potato. Same molecule, different shape, completely different job in the world. And that really just leaves you with one final thought, doesn't it? We've just peeked into the incredible, hidden complexity of one of the simplest nutrient molecules there is. It really makes you wonder, what other astounding, shape-shifting secrets are just waiting to be discovered inside the even more complex molecules that make us who we are?